It is science o'clock. It's time for a new lesson, and we're doing current and resistance. So last lesson we did a thing where we talked about electric current and electric and charge. Today we're taking the current a bit more and linking it to resistance. Just note this doesn't really match what's in the book or how the specification spreads out. I've kind of broken it down into smaller bits to make it, I think, a bit easier to understand, but maybe I'm wrong. But yeah, so if you've got the textbook, they do like what they do over one double page spread. I was thinking of like 3 lessons because I think it's very important to know this stuff. So we're going to be able to describe what resistance is, hopefully, and how it affects the flow of current in a circuit. But for the starter, I want you to do the following things. So carrying on from last lesson, can you draw a circuit, the circuit symbols for a light, a cell, a resistor, a battery, and an ammeter? Just the symbols. You don't have to put them together into a circuit. Then I'd like you to state the following quantities: current, charge, time, energy, what they are measured in. I missed that part out. So what is current measured in? What is charge measured in? What is time? And what is energy measured in? Can you then give me the equation that links current, charge, and time? And then can you tell me the symbols that we use to represent current, charge, and time? Pause, write down the answers, go. Excellent. Shall I go for the answers for you? Okay, get my pen at hand. Okay, first one is a light. Nice and simple. Why is that not working? There we go. It is a circle with an X in. A cell looks like this. A long line and a short line. Carrying on like that. Resistor, hopefully you remember from yesterday's lesson, is that is terrible rectangle, and I apologize, but that is what a rectangle. A battery is just multiple cells joined together. And an ammeter, a circle with a capital A in the middle. What are the units for the following quantities? Current is measured in amps. Put that down as an A. Charge is measured in coulombs. Coulombs. There's a U there that I've missed out. And that's a C. Time is in seconds. It's a small s. And energy is joules. Yeah, check. What is the equation that links current, charge, and time? Now, I should have done question 4 and question 5 in the same, in the other order, because I'm going to give you the answers to 2, but the letters used to represent them are Q equals I T. That is the equation that links all 3. If you want to put it into the little pyramid, triangle, here's how it goes. Boink, 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 Q, I, T. Did you get it right? Well done. Okay, let's just have a bit of a review. Current is a measure of the rate of flow of the electric charge in a circuit. Remember, I think last time we mostly talked about what the electric charge was. The electric charge was electrons, but you can have other things like ions flowing through a circuit. But for most of this, we're going to think about it in terms of electrons because it's easier. And remember, electrons have a charge. What's the charge of an electron? It's negative. And that charge, how much negative charge they have, is measured in coulombs. And so we measure the charge in coulombs. We know current is measured in amps, amperes, using an ammeter. And the definition is if you have 1 amp, is 1 amp of current is 1 coulomb flowing every 1 second. 1 amp is 1 coulomb flowing every second. And this is an important little fact. Maybe if you want to write something down, one of these things is important. If you're making a circuit, if you're drawing a circuit, or you're building an electric circuit, and you put an ammeter in, you have to put the ammeter in series. In series, remember, is when you just have like a loop, like this. If you put an ammeter in, you must put it in the loop. If you put it outside the loop, like this, which is classed as parallel, it will actually break the circuit. It will do something called a short circuit, meaning the circuit won't work, probably get hot, maybe even catch fire. So don't do that. So you must do that as a, you must, when you're adding an ammeter, add it in series. Okay, so we're going to look at what resistance is. Maybe we go back last lesson, in fact, last week. What is the structure of a metal like inside? If you're looking at the atoms, what does it look like? What did you say? You said the metal ions all arranged in neat rows, and then there's a sea of delocalized electrons? Yes, that's correct. Well done. Here we have a zoomed in version of an atom. Now, it's very zoomed in, obviously, but also it's missing, like these atoms would be, it's missing a lot of details. But here's a good example. So the slightly bigger atoms, the slightly bigger circles, are the copper atoms. I can't draw on this. Are the copper atoms. The slightly bigger circles are the copper atoms. Use the mouse pointer. Copper atoms, the big ones. There they are, and they're fixed in position. They're nice and regular. The little black dots, or the grey dots, they are the electrons. And hopefully you notice that the electrons are moving along. They are moving along the wire. Where's the arrow gone? Oh, cursor's gone. There it is. So the electrons are travelling along the wire in this direction. They are flowing. So therefore, we have an electric current. Those electrons are flowing down. We have an electric current. But what do you notice about the electrons as they travel down? What's happening to them? What's their journey? Their journey isn't a nice, smooth transition along the wire. No. They're bumping into the atoms. And they're bumping into the atoms, and therefore it's harder for them to get down the corridor. Their wire. They are being resisted. It's kind of like in school when you're walking down the corridor. If there's no one in the corridor, it's really easy. You can walk from one end to the other. If you're walking down the corridor and it's a lesson changeover and it's packed, it's much harder to walk down the corridor. Excuse me. You keep bumping into people, and the more people you come across, the harder it is to go down that corridor. And it's exactly the same for the electrons in the wire. If there's things in the way, it's harder for them to travel. If there's nothing in the way, it's easy. Okay? So, this is basically the definition of what resistance is. Resistance is how easy or hard it is to flow down a wire. So we know that electrons go along the wire, but sometimes, or all the time, when they go along the wire, they collide with the atoms, because everything's made of atoms. So they collide with the atoms. When they collide, that causes those atoms to vibrate a bit more. We know that, and therefore the metal gets hotter, and so you're walking down the corridor, you bump into someone. That bumping makes them move around, means they take up more space, so it makes it even harder for you to get past, or other people to get past. So this is kind of thing. So this electron flow and resistance, when electrons flow, they make the metal have a resistance. Also, the resistance stops the electrons flowing. So those two things are kind of linked. But basically, resistance, here it is in blue. Where's the cursor gone again? Resistance is a measure of how much a material tries to stop electricity passing through it. A high resistance means it tries to stop the electricity a lot. A low resistance means it doesn't try to stop the electricity that much. It's worth noting that pretty much every single thing that has electricity flowing through it has some resistance. Even the best copper wires will have a little bit of resistance. And that's why over time electrical things get warm, because when those electrons collide with the atoms, the collision causes the atoms to vibrate and get them a bit warmer. And so if you leave something plugged in for a long time, your phone charger, if you put your hand on your games console, after it's been on for a while, you'll feel it warm, and that's because the flow of electricity, the electric current, is bashing to the atoms and the ions inside, causing them to vibrate and making them hotter. Okay, so here's a little animation. First of all, we've got a battery, a 9-volt battery, a resistor down the bottom, and an ammeter. Now, what's happening on this animation is I'm increasing the resistance of this resistor, and as I do that, look what's happening to the electron. I'm going to go back and then hopefully restart the animation. Oh no. There we go. So current's flowing, you can see those electrons going really fast. The battery doesn't change, but as I increase the resistance, so it's 3 ohms, 3.5 ohms, 4 ohms. Look at the current and look at those electrons. As the resistance goes up, the current goes down. As the resistance goes up, those electrons move slower. That's what resistance is for current. Resistance is something that slows down the electrons. So if you keep getting the resistance higher, those electrons slow down, and as a consequence, that current goes down, because how fast the electrons are is completely linked. It's going up really fast, so fast, how fast it is. And those electrons are almost stopping. So as you increase the resistance, you slow down the electrons, and you reduce the current. Check. There's a little note. In a series circuit, if you increase the resistance, the current will decrease. And that makes sense. If you think about it like the obstacle, like walking down the corridor, if you have one person in the corridor and you're trying to walk along, that will be fairly easy to get through. If you have 2 people in the corridor, it'll be still quite easy but harder. If you have 100 people in the corridor, it's much harder for you to get through, so it will take you longer. If you increase the resistance in a circuit, the current will decrease. Write that down. Oh wait. Done? Excellent. There's a link to this. All this is linked. Now this is tricky. Like I said, I've mixed these things up. I've done it in a slightly different order because I think it's easier like this. But there's an equation. The equation that links resistance and current also adds something else in. It adds something called, you probably heard it called voltage, but in reality we should call it potential difference. But I'll probably do that in the next lesson. So today we'll just write it down as voltage, but be aware I might refer to it as potential difference. I'm not tricking you, it's just the way it is. Okay, so voltage is equal to current times resistance. V equals IR. In fact, we can even put it into a little triangle. Boink, boink, boink. V, I, R. And hopefully you can see from this equation here, when we had that last animation with the circuit, the voltage stayed the same. Because where did the voltage come from? It came from the cell. So if the cell stays the same and then the resistance kept going up, well, think about your mathematical skills. If the resistance is going up and this stays the same, this one has to go down for that to balance. I've just drawn over the notes. I apologize. What are the units of voltage, currents, and resistance? We know voltage, or potential difference, going down there. Potential difference is measured in volts. Current is measured in amps. Resistance is measured in ohms. After a man called George Ohm, we'll look at him another day. So pause, write those down. They're really important. Write them down. Go. Good. Okay. I've just done that. So here's a couple of examples. A filament bulb has a current of 20 amps running through it with a potential difference of 100 volts. What is the resistance? So V, I, R. So we've got 100 over 20, 5 ohms. 5 ohms. The symbol for ohms is this omega, capital omega symbol. So here's an opportunity for you to try the equation. You'll need a calculator, or you need to be really good at maths. Shall I do the first one for you to help you out? Let me put a little triangle up here. Oh, that's terrible. V, I, R. Okay, we know V is 230, and we know I is 10. And the equation is V over I is R. So 230 over 10 is 23 ohms. I'll leave that for you to do. Pause, do those, and give you the answers in another lesson. Pause. Done? Excellent. Okay, now I need to teach you the rules for current in series. And this is all about what happens when you change a circuit. Okay, so here's a nice simple circuit diagram. What do we remember about those electrons flowing around? The electrons are flowing around. Look at the speed of the electrons. Is it anywhere faster than anywhere else? No, the electrons all travel at the same speed in the circuit. Okay, so if you're traveling in a circuit, the electrons travel in a circuit, they travel at the same speed everywhere, which links to the rules. The current is the same everywhere in this series circuit because there is only one route for the electrons to travel. My head covers the word route. And if you look at that circuit, so here we have battery, and we have 3 ammeters placed around the circuit. Ammeter number 1, ammeter number 2, and ammeter number 3. And because it's a series circuit, whatever ammeter 1 reads, one here, ammeter 2 and ammeter 3 must also read. Those are the rules. Whatever ammeter 1 and then ammeter 2 and then ammeter 3 read, it must be the same in a series circuit. This is 1, and 1 is 1, so 2 is 1 amp, and 3 is 1 amp. In a series circuit, it must be the same current everywhere. Let's see what happens now. So here we have another example. If this is 3 amps here, well, what are these two going to be? It's a series circuit. There's only one route for the electrons, so this one has to be 3, and this one has to be, that's not 3 amps too. What about this one? The one at the bottom says 11. If it's 11 at the bottom, series circuit, current is the same everywhere. This one has to be 11, and this one also has to be 11. Current in the series circuit is the easiest of all of the rules. But there are other rules, so they can get confusing. But this one is the simplest. So I thought I'd start with this. Excellent. Aha! Now it gets a little bit trickier, but not too much trickier. Okay? So remember, where do the electrons get their push? What pushes the electrons around the circuit? I'll flip that, get that animation going again. Where do they get their push? The battery here. The battery gives the push. Okay? So, come on. The battery gives the push. Now, we see the electrons traveling round the circuit down here, and then, can I replay this? Okay, when you get here to this junction here, can you see where my little pointer is? Oh, I can draw over it. Sick. Oh no, but now I can't replay it. There we go. So see, when they get to this junction here, look at the electrons. One goes to the right, and the next one goes down. Let's replay again. Come on. They go down, they go right, they go down, right, down, right. So they're splitting, they're alternating. Okay? One of them goes along one path, the other one goes along the other path. So that's a really important thing, yeah? The electrons are small, tiny particles. So when they get to a junction, they have to choose to go one way or another way. Okay? In this section, both those bulbs are the same. So the electrons, one chooses to go one way, one chooses to go the other way. We can look at more complicated versions later, but now let's go look at this corner here, yeah? Hopefully I haven't drawn over it too much. Look what happens. So the electrons from the first avenue join, and the ones from the bottom join. Let's put that back on again. And so here, the two electrons come together, the two roots come together, and we get the current back up here. So it starts here like this, and then it splits. Some goes this way, and some goes this way. And then when we get back to this junction, the electrons from this section and the electrons from this section meet up, get back together, carry on around the circuit going like that. Okay, so let's see what happens to the rule with current in a parallel circuit. The current in a parallel circuit splits when there are different routes for the current to take. The current that goes into a junction must be the same as current that leaves a junction. My head is in the way, sorry. If the bulbs are identical, equal current will flow in each case. So, if you have a current of 2 amps leaving the battery, then when the current gets here, some of it goes this way and some of it goes that way. So let's call this A1, we'll call this one A2, A3, and A4. So what you must have is A1 must be equal to A4. Whatever comes out of the battery has to go back into the battery. And A2 plus A3 must be the same as A1 and A4. As in, if you add this one and this one together, they have to be the same as this one, which is the same as this one. Okay? So whatever comes out goes in there. Note this is a simple version where this route and this route are the same. If they were, one's a bulb, they're both bulbs, light bulbs, yeah? If one was a bulb and one was a resistor, it might not be 1 amp each, it might be divided differently, but we'll come to that another time. So here's another example. If you get 4 amps here, and what do you get here? Well, this is coming out of the battery, this is going in, so this also has to be 4 amps. If this is 2 amps, what is this one going to be? Note, the example here isn't going to be the same as always. It's 2 here. What you notice, if this is 4 and that's 2, 4 minus 2 is 2 amps. So this one has to be 2 amps. So these two are the same, but they're not always going to be the same. What matters is that plus that equals that. These two together must be equal to this. So in this case, they're both 2, so it's handy, but it's not always going to be like that. Let's hear an example. Okay, so this one, 6 amps. So what is this one going to be? Going in has to be the same coming out. Now these two bulbs, I'm saying, are the same, but what if they were different? We could have this one, if I decided to put this one as 4 amps, what would this one have to be? That one would have to be 2 amps. Because 4 plus 2 equals 6. Okay, so here we are at the end. And all that matters is now for you to practice this. So we have a series of simple circuits. We have an example here. I'll do one example for you. Okay, so here we have number 2. So I would suggest you draw this circuit down, and then where the letters are, you write the values that should be there. So here we have 4 amps here, so that's 4 amps going out of cell. So here, this is going back in, so this has to be also 0.4. I said 4, but I meant 0.4. And then here we've got 0.2 going down this route. So we have 0.2 going down this route. So 0.4 minus 0.2 is also 0.2 amps. So 0.2 plus 0.2 does equal 0.4. They're not always the same in both of those branches, so be aware. Don't think if that one's 0.2, that one has to be. It is in this case. So draw those other circuits, write down the answers for the missing values. I will give you the answers in another lesson. Do that. Pause, write those down. You've done all of those. There's another set. Trick 2. Okay, do the same. A little bit trickier. 3 branches. So, write it down. Notice this one here. 0.1, 0.3, 0.3. They're not always the same. So, just note. Okay? Draw them, write the answers. Give you the answers another lesson. Okay, love you. Bye.